we did force problems, when we first started doing force problems, we started by saying, let's look at cases where the forces are balanced, and we're going to do like a translational equilibrium. When we started doing the rotational version, when we started doing, torque, we looked at, let's figure out what it looks like when our torques are balanced and hit rotational equilibrium. After translational equilibrium, back to forces, we looked at Newton's second law, which said that the sum of forces acting on an object was equal to mass times acceleration. Now we are going to get a rotational version of that. The sum of torques, instead of the sum of forces, is going to be mass is replaced with the non-linear inertial term times an angular acceleration. So this gets us into the idea of rotational dynamics. Rotational dynamics is just looking at torque type problems, rotation type problems, where our acceleration, in this case our angular acceleration, is not zero. So let's look at what this means. We can say maybe I have a wheel like this, and I'm going to give this thing a radius of capital R, give this thing a mass of capital M, and we're going to put an axis right through the center of the wheel. I would like to pull with a force right here. And I'm going to put that force some other distance, little r, from the center of the wheel. If this wheel is a solid cylinder, which I'm assuming it is, I can actually just say, you know what, it's some kind of a round shape, it's got some kind of a gamma, then I can find the angular acceleration of this wheel. I can start by saying I need a sum of torques. I only have the one force, so the torque exerted by that force is equal to the perpendicular force times the distance. Now this force I already drew as perpendicular. Right here is that distance, and that's already perpendicular. So my force is going to be F times little r. That's how far that force is from the axis, and that's the only force acting. Sum of torques is equal to, and again I'm just kind of trying to remind you, this is just like saying sum of forces is equal to whatever the forces are, and then we set that equal to mass times acceleration to solve for acceleration. Let me do it this way, to solve for acceleration. Now I'm going to do the same thing. Sum of torques is equal to, these are the torques, and that's going to be equal to the moment of inertia times the angular acceleration. That's really the bulk of what I'm doing with this. I'm solving for angular acceleration, so I'm going to say angular acceleration equals force times r divided by moment of inertia. So force times r divided by gamma mr squared, and that's an angular acceleration. I can keep running from there. I can figure out, what does it look like if this force is acting at the outer lip when this r and this r are the same, and I can cancel some things. I can say this thing starts at a rotational speed of, 0. It's going to have this force for a certain amount of time. Let's find how fast it's moving at the end of that time. I'll run through some examples in a separate video, but this is the idea of rotational dynamics. We are just saying sum of torques equals I alpha, and it's going to be a whole lot like saying sum of forces equals MA.